This morning we want to start with one of the foundation in modeling that we normally teach when we want to. It's a kind of an overview of modeling and analytics. Yesterday we were looking at climate and public health, but today we are going to be looking at the overview of infectious disease and malaria modeling. It's not working. Can you scroll down? Next slide. Now, actually, mathematical modeling of malaria, especially malaria, did not start from a mathematician. It was started by a medical doctor whose name was Ronald Ross. Ronald Ross was the father of mathematical epidemiology. So, and he made a statement in one of his first paper. Said, as a matter of fact, all epidemiology concerned as concerned from time to time or from place to place must be considered mathematically. However, many variables are implicated if it is to be considered scientifically at all. Now, if anything in epidemiology is going to be considered scientific, it has to be considered mathematically. Now, he further said, to say that a disease depends upon certain factors is not to say much. Now, before now, in epidemiology, people say that, this disease depends on, they always look at factors like yesterday we were talking about the risk factor for malaria is the Anopheles mosquito. For lung cancer is smoking and of that. So they always talk about factor, and then when they talk about the factor, they are looking at correlation. Or correlation means association, regression means relationship. So these are two different things. They look at those things from different points of view, and then they plot the graph, and then they do some descriptive analysis, and then they publish paper, which is not really saying something deeper about the problem at hand. So he now said that now to say that a disease depends upon certain factors is not to say much. That means you are still on the peripheral, surface level. When you are, so that's why now, as good as statistical models are very good, but they can only capture things at surface level. You understand? Statistical model will start from it, but that's not the end, because they cannot really see the underlying mechanism that is producing transmission we are seeing. So we normally start with statistics, and then, but for you to see stronger thing, you need to do a lot of mathematics, and then try to use mathematics now from the point of view of quantitative approach, right? So now, until we can also form an estimate, estimate of how largely each factors influences the whole result. We are saying that climate affects malaria. Can we find the estimate? How large is climate affecting malaria? When we say temperature, how large? When we say rainfall, how large is rainfall affecting malaria? How large is rainfall affecting the disease in question, CSM, cerebrospinal meningitis, and all of that. So now, and the mathematical method of treatment is really nothing but the application of careful reasoning. Careful reasoning. Who is fiddling with the pointer? Somebody is fiddling with the pointer. Where is the pointer? Please get me the pointer. So, like, careful reasoning is stronger than mathematical rigor. Now, a lot of us believe that, but the stability in that, and then you are trying to do mathematical rigor, very good. But now most of the mathematics we use in epidemiology in terms of the qualitative aspect, like you can do modeling, analysis of modeling. When you have a mathematical model, you have developed a math model. So there are two directions you can go in terms of its analysis. You can go qualitative, and then you can go quantitative approach. This is another approach, right? So this approach, the qualitative approach is tends towards the theory of nonlinear dynamical systems. Majorly, people who are doing mathematics here, some of them will know what I'm trying to talk about. I'm still coming to tell you something. Some of us who are not doing math. So I'm marrying the two audience together. Now, you find for the qualitative, you are building theory around nonlinear dynamical systems, and you are discussing issues that borders on the qualitative behavior of the model system you have developed. Now, as good as this may be, very wonderful, is not enough. Why is it not enough? Now, you will do all the mathematical rigor, like the production number, you find the equilibrium analysis, you do the global stability, you engage with local stability and all of that. And then you also do maybe bifurcation by using all those different kind of, but you find out that all those methods, they are already established. You are just using them. They are not your own primarily. Are you getting what I'm saying now? So we just use them, and then you also try to use your model to do the analysis alongside. That's qualitative. But most of the time, we find out that when we do all this, if you bring out 20 papers from mathematics model, you find out that all of these things, you will see them, they are the same. The same. So which means that what we have been doing so far are just traditional analysis. Those are what I call traditional or classical analysis of the model, which does not inform policy. Now, the aspect that inform policy, which is one of the reasons why we are here, we want to change the trend in Nigeria, is the one that when you use quantitative approach, quantitative approach, right? Quantitative approach. Now, when you are using quantitative approach, you are making use of data, real life data. You are making use of real life data. So, and then in those issues, now doing these aspects is what this guy was talking about, saying that the mathematical method of treatment is really nothing but the application, underline the word application, of careful reasoning to the problem at issue. So when your model is not really addressing what is going on in the real world in terms of the location, in terms of the population, the demography, yes. So it's not really, nobody is using it. It's going to be a useless venture. But if now you want to use your model to address what is going on in the public health space, then you may also, apart from doing these aspects, qualitative approach, especially for mathematicians who are interested in mathematical rigor, you need to focus on. So you can have two papers. Like in my center, what we do is, because we are mathematicians from background, and then some of the students who are coming from mathematics departments, they will need to show some mathematical rigor and all of those ones. We have them. I was telling somebody yesterday that there are some work we have been doing for the past 2 years, 3 years. When it comes to data work, a policy-driven model, there are some work we have been doing for the past 2, 3 years that we have not finished because it has to do with policy-driven work. You cannot just, it's like you want to produce drug for large population. You just sit down in your house and be mixing chemical together. No way. Oh. You people will die now. You know the number of people that die using the fake drugs, even children and all that. So that one has to go through serious feedbacks from the programs before it will be eventually accepted and published and all that. It takes time. But this one that I just come to my table and we develop model, I told them that, look, if we are doing that one, by now we'll have published like maybe 2,000 papers that are useless. 2,000 papers. We'll just be, as we are here in this place now, within morning and now, we can develop about 200 models. And then I'll just give each one of you. You'll be working on it. And then we'll be throwing it to publication. Everybody will just be happy. But it's useless. Are you getting me now? So it's time to go in the another direction. You are there in Lafia, in Nasarawa State, and there is an epidemic. They say, where is the modeler here? You are showing them stability. They will run from you. Say, what are you talking about? You are not speaking the language. Are you getting me now? So that's the problem. So it's like, just like what Daddy said yesterday, the mathematician or mathematical modeler is you are completely out of the society. You are just there in one space. You are doing your own, and then the whole society, they are doing their own. You are not relating. So that's why we are saying the aspect of quantitative is very important, the quantitative approach. And that was what Ross was talking about, that the mathematical method of treatment is nothing but careful reasoning. So careful reasoning is more important in this matter than mathematical rigor when it comes to application. Let's move on. Where is the okay? Now, what's the motivation? Mathematical modeling plays an important role in ordering our thoughts and shaping vague intuitive notions. Now, there are two worlds. We have the conceptual world and then we have the real world. In the conceptual world is the world of ideas. You sit down in your office and then you are thinking that, okay, I want to model kidnapping in Nigeria, and then you are bringing X and Y together. You said that this population is X and that population is Y. And then, like we can model kidnapping here now. Very simple model. I will say that the X is equal to the prey. Those are the people that are being kidnapped. Y are the predators. So the predators are preying on the prey, right? And then, anytime they come, they kill all the prey. And then when they kill the prey, the population of the prey is declining. Are you getting what I'm saying now? And then in the long run, if they continue like that, the population of the prey will not exist again. There will be extinction. Right? If nobody does anything. So what will now happen? We need to put control into that model. So what are the control we can put to stop the predators? Are you getting what I'm saying now? One of the ways is that we also have to create maybe the government policy have to come around that and begin to. So these are things to discuss about maybe during our short meeting. How we can discuss how we can model prey predator just with a prey predator model. So we want to model kidnapping or banditry. Just with two system of models can capture it to start with. And then we put control, and then a lot of things we begin to see what are the control available to reduce this kind of killing in our environment. And then we begin to think around it. And before we know it, I think some solution can come out. I don't know. So, but this kind of thing, we don't have the data. But what we can also do here is to see into, like something is going on. It's like an epidemic. It's going on in our environment. Well, we don't understand the dynamics. You understand? So we need to understand the dynamics. How is it? How is the evolution of banditry in Nigeria? What is it? What is it? So let's look at it. So now, understanding the dynamics will make us to begin to think that, oh, so if this thing continues in the next 30 years or 40 years, what's going to happen to the population? We are going to see. Now, if it stops, how can it stop? What are the ways to truncate it? So these are questions we must put into the model, feed into the model, and then the model will bring out what we may, what's some of the way out that we can bring out. So now you are trying to, you have scattered thoughts. Scattered thoughts. Thoughts are coming from different directions. Modeling can help you order your thoughts. You understand? Your thoughts are ordered. Now, how is it ordered? In mathematical language. You understand? So now your model is not supposed to be more complex than the real world. If your model is too complex than the real world, then it's not model, because the model is an approximate of the real world. So if you are modeling something, it's so a model is to simplify, because the real world is complex. Understand? The real world is very complex. It's a complex system. A lot of stochasticity is going on, stochastic fluctuation, white noise, and all of that in the whole population. As we are here now, you know, a lot of non-linear dynamics that we cannot really explain. Now, model comes in and we are saying, okay, let X be this, let Y be that, let Z be this, and then you are representing each person with a particular variable and all of that, and then you are seeing things. So, and you are able to understand what is going on in the system. Now, initial models are verbal descriptions that tend to become insufficient as soon as the scenarios become complicated. So the models that have been built in the medieval, people have built models in the medieval, and they have not really been able to help anybody at certain time, because what happened is that as the real world is becoming more complex, you know, like initially when God created the world, we had only two people, two persons, right? So from one person, right? One, two, and then it started growing. The population started growing exponentially, until they. Now, as the population is growing, the complexity of human being is also playing around in terms of human behavior. You know, now many of the times complexity comes for human being because of knowledge. Your soul is the seat of knowledge. The knowledge you have makes you to be more complex, even yourself. Yes. Now so you said no. How can I take the drug? What do you mean? You argue, and then even though the person is very small in body, like this, small, tiny, but the knowledge that is sitting inside him is bigger than his body. So he's seeing a big man inside. What do you mean? What do you mean? That one say, what do you mean? And then fight start. The mother told the child, so stop throwing stone. Say, hey, well, no problem, I'll stop, but I'm still throwing it in my heart. You see complexity. As people are growing, everything is becoming complex. So what do we do? Initial models, verbal model cannot do the work. Again, we need to do mathematical model. Yes, let's see. So mathematics provides a powerful language that forces us to be logically consistent. Underline that. Logically consistent and explicit about assumptions. So you are forced to do it logically, not anyhow. A lot of people are doing many things. That's why you see now, if you are doing something and it's not according to the global principles or the conventional way, then you are not going to affect anybody. You are just it's like you are playing within your community, and then you are just doing things to make yourself happy.
So when we say it provides a powerful language, and that's why when we are defining mathematical model, I love the way that you define it yesterday. I say, wow, this is our normal definition. So when you define a mathematical model, so a mathematical model, can somebody remind me the way you defined it yesterday? If you listen to everything, because me, I listen to everything. Yes, mathematical. How did you define mathematical model? You were not listening. Oh yeah, now. How did you define mathematical model? Yes, sir. I'll remind you. Don't worry. Before I remind you, I want somebody to. Okay. 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 Yeah. You are close, but you are not there. Okay. It said that mathematical model is a representation of the real world with mathematical terms and language. He used the word language. You remember? So, so it's a representation of the real world. A mathematical model is a representation of the real world with using mathematical terms or language. Right? So you have the real world, and then you are trying to use mathematical language to represent what you are seeing in the real world. That's a mathematical model. Right? Now, the real world is where the question comes from, not from maths. The language or the method of responding to the question from the real world is from mathematics. Right? So, we are saying here it's a language that forces us to be logically consistent and explicit about assumption. Now, over the years, we have encountered very interesting and inspiring and challenging discussions at the end of workshops on infectious disease modeling with the following recurrent themes. One, while most disease transmission models predict an expected exponential growth at the beginning of the epidemic. So what's an epidemic? Yes? What's an epidemic? Huh? What kind of outbreak? I don't want a chorus answer. What's an epidemic? Yes? You raise up your hand and you tell us. What's an epidemic? Yes? Epidemic. And what kind of outbreak of disease? Huh? There's a word, there's a particular word you didn't mention. Yes, I know it's an outbreak. It may not be infectious disease, it may be even non-infectious disease. It may be outbreak of anything, outbreak of noise. Yes, but there's a word. Yes, yes, I know there's a word. It has to be. Epidemic means short outbreak, short outbreak, and pandemic means what? Global outbreak. Global. That's why COVID was pandemic. It was a global thing. So epidemic is short and localized. You understand? In a local, maybe within a country. But pandemic is a global thing. Okay? So disease transmission models predict an expected exponential growth at the beginning of the epidemic. That was what I was showing yesterday. When an epidemic starts, it continues to grow like a velocity time graph. It's growing like this. And then as it's growing, we don't know when is it going to come down. Do you understand? So the question the public health people are asking is, when is this growth that we are seeing, when is it going to come down? We are seeing an upward trend. So it means that a lot of people are being infected. The number of infected population is increasing exponentially. So, and that was why I drew the picture of Arnold yesterday, like a tree diagram, you know. So, and then one person can at least infect two persons, and then the tree was growing exponentially. So, as people are getting contact with infected persons, they are getting infected and they are entering the infectious class. And then over time, the number of people that are infected is increasing. So what we are saying is exponential growth at the beginning of epidemic and empirical data often exhibits sub-exponential growth patterns. How do we best characterize these non-unique sub-exponential growth functions in the context of infectious disease modeling? These are some of the questions we'll be answering in this summer school, this school. So how do we characterize, how do we describe these non-unique sub-exponential growth functions in the context of infectious disease modeling? We are seeing a growth function moving, like captured like a straight line and moving up. And then the question is, when is it going to go down? At certain times, it may even exhibit a steady state. You understand? So in this steady state, it means that at this level, just like your velocity time graph, the number of people that are infected remain constant. It may be due to many factors. When you see this kind of, you see, when you are looking at graphs, when it comes to epidemics, there are lots of things around it. So that's why you need to understand a lot of biology and factors. When a graph is behaving certain way, it's not just behaving like that. There are underlying things, mechanisms that are making it to behave like that, and then you need to get, and that's where the aspect of understanding the biology is important. So it could be that at that state, maybe a measure has been put in place. You understand? And then the disease remain on a steady state. It's no longer increasing, but it's steady within particular time. And then at certain time, it started dropping. So when it's dropping now, what is going on? It means that a further control measure has been put in place. Do you understand? Like for COVID now, we said social distancing, face mask, and then all of that, non-pharmaceutical intervention were put in place. And then, people, the rate at which people are getting contact is reducing. People are not in school. People are not going to church normally where they can cough and collect COVID and all that. So they are reducing contact between human beings. So now, are there many, even infinitely many mechanisms that lead to the same or very similar sub-exponential growth functions? Do we have other things that are contributing to that growth that we are seeing? Does a slower than expected initial growth at the beginning of the epidemic imply a smaller value of the reproduction number? Now, when the epidemic growth is slower compared to the one that is faster, so does it affect the reproduction number? That's it. I mean, that is true, actually. Because, like we said, that at least one person can infect two persons. So if the epidemic growth is not very fast, then the R naught will also be affected. So that is the average number of secondary cases that will be produced by one primary case will be lesser to when the growth is faster. So now, okay, we discussed this quantity yesterday. Now, what exactly does it mean when we say deterministic models approximate their stochastic counterparts by the law of large numbers? Now, these aspects will be, like in this meeting is focused on two areas of methodology. We have the deterministic models, and then we are going to be having stochastic models training. Like, because the thing is, most of the disease we have been capturing, we have been using deterministic model, which is OGE, ordinary differential equation, right? We have been using OGE, especially first order ODE, to capture disease dynamics in Nigeria, initial value problem, right? But this time we are also going to look at the aspect of stochastic. The reason is because we have seen that for small population, you cannot use deterministic, or when a disease has just started, you cannot use deterministic to capture it. Now you can only use stochastic because of the noise, the randomness, the function. Now, there is one flaw or one disadvantage of stochastic over deterministic model. And one advantage is that the stochastic model capture the noise in the disease spread and even the data. Every data has some level of noise, some stochastic fluctuation and all that. The noise are the random error. Yeah, the random error, the variabilities in data. You understand? The variabilities in data. Stochastic has the ability to capture it. Now, if I'm working on a stochastic model now, take for instance now, for a stochastic model, I want to capture those people that are infected, number of infected human, right? And then the time, right? Now, for a deterministic model, I'll be saying that it's growing like this, something like this, growing exponentially, right? This is the way it grows like this. Maybe this place is 0, 1, 2, 3, 4, and 5, right? And then the x-axis is also 1, 2, 3, 4, 5. Now, what happened is that it's growing. The eye is growing. But it's giving us single value when the number of infected human is 1. At what time? At 1. At t equals to 1, number of infected is 1, right? It's just only 1. But for stochastic models results, now it's going to give me several values at intervals. So now this one now is going to be, if I'm running a stochastic model, it'll be like 100 simulation. So at the end of the day, at t equals to 1, I'm having several values for number of infected. So when t is equal to 1, I can trace it, like I can trace it from here, trace it from here, because I have all these figures like that. So at the end of the day, the number of infected at t equals to 1 may range from 0 to 2. Right? But for the deterministic, at t equals to 1, the number of infected is what? Is 1. That 1 is still within this interval. So it somehow give an interval estimate, not point estimate, which normally when you are predicting, if you are traveling from Lagos to Abuja, now there is always a forecast that this within certain interval of time, every good forecast is given at intervals, not at point estimate. Because there is possibility, because of variation, that you didn't get there, and that, so it's plus or minus 1. So when it's saying that the plane is going to land, when you are going, the estimated time of the flight is 40 minutes. You understand? It's 40 minutes, so it's 40 minutes plus or minus x. Because some issues can come up in the air or some delays. So they have to factor it. So there's a bound. Even when somebody is going to expected date of delivery for so people who have been people, for women that give birth, they give you expected date of delivery, right? But it's also an interval estimate. Do you remember that? So interval estimates are much more better than point estimate. Because if you say you are going to give birth in 9 months exactly, it may not be. Some variation can happen. And you get to, and so that's the power of stochasticity. It gives you an interval estimate, that even the one that we estimated falls within that interval. So we look at that. So let's okay. So we are saying here that deterministic models approximate their. So now, when the population becomes so large, very, very large, there is what we call the law of large numbers. It makes the stochasticity to reduce to deterministic. And that's what we are saying here, that now deterministic model becomes the approximate or stochastic counterpart by the law of large numbers when the number of the population is getting large or the disease. So now, when we say law of large numbers, are we referring to a population that is infinitely large or something else? So we need to also define that as we go forward. Now, which features of the population-based model in which the exponential division is assumed at the individual level can be generalized with non-exponential distribution? That's the transmission model, transmission rate. Now, you know, most times the transmission rate is beta, right? We usually use beta, right? Most times we define it that under the probability of exponential distribution. You know, like the transmission rates, we are saying that it follows exponential distribution, which in real life it may not follow exponential distribution. Exponential distribution is saying everything is going straight up, but real life may not put that because of certain factors. Now, there are certain factors that can affect the transmission rates. One of them is social factor. Social factor in the sense that if I have an understanding about the disease, I know what I can run away from. Do you understand? I may not be infected. Do you understand? If I have some level of hygiene, I may not be infected. Do you understand? So many things can affect the transmission rates. So the transmission rates, we are saying in the real sense of it, it can follow other distribution like Poisson distribution. Better and follow Poisson distribution. We will be looking at this practically as we go on. Poisson, or it may follow the Poisson distribution, or follows a gamma. Normal, you know, gamma is normal distribution. The one you did like this, like a bell shape. Bell shape distribution. Yes, can follow that kind of distribution. Now, the simplest one we have been using is the exponential. Everything is going up straight, but life is not like that. Life is not a straight line. Even for you to get from Ekiti to this place, is it a straight line? So let's go back to this thing, the slide. I think I need to move fast. So what do we mean by a case? When data from outbreak, investigation, and surveillance are presented as time series of number of cases. What do you mean by a case? Yes, who's going to tell me? You know, during COVID, they will announce on the radio, we have seen one case. So what do you mean by a case? Yes? Yes, an infected person. That's a case. So, our generation intervals consistently defined across literature in epidemiology and infectious disease models. What's generation interval? The period between when somebody is infected and then also infect another person. That's generational interval. You know, like this guy had contact with the infected person and then is infecting another. We are producing another secondary case. That's generational interval between one generation and the next. That's generation interval. So how do we characterize and compare variability among random variables, such as infectious periods? The infectious period for what is infectious period? These are biological things, or the number of secondary infection transmitted by a primary infector. So infectious period is a period between the time you are infected, right? And the time you begin to do what? To show symptoms. That's infectious period, right? So, is this no? And the end of the infectiousness, and that one is incubation period. The incubation period is the time between infection and the time you begin to show symptoms. It's incubation period. The infectious period is the period at which you are infectious, and the end of the infectiousness. So that's why the infectious period is equal to the inverse of the recovery rate, right? So the recovery rate is equal to 1 over infectious period. So you can find the recovery rate from the value of the infectious period. So the infectious period for malaria is what? For malaria. Okay, continue to think about it. Now, let's move. Mathematical modeling is an abstract representation of a system based on mathematical terms in order to study the effects of different components and consequently to make predictions. Now, after bringing out the mathematical terms, representing it, the plan is also to study the effects. You want to study the effect of one, maybe one factor or one component, how they are influencing each other in the model. And then you want to also make predictions. And then the development of mathematical models depends on several factors, such as you have your data at hand, your data, and then the hypothesis to be addressed. You have a question. Now, modeling is good when you respond to it from the point of view of questions. Now, yes, and the experience of the modeler, the experience of the person you are working with also play a lot. Now, it's like you are traveling, and then somebody has, like some of the drivers that drove us from the southwest, many of them have experience of this direction. So they know where to pass. They know the road connection. Now, if some of us have to bring our car down to this place, it may take us more hours because we are not experienced. So once model parameters are fitted with experimental data, mathematical models have the capacity to serve as virtual clinical trials to uncover the success and pitfall of treatments, and as well as vaccines. So they are very powerful too, especially when you are fitting a model to data, experimental data, and then it can be used to uncover the success or pitfall of treatments or as well as vaccine. What do we mean by that? Now, you are trying to, just like during COVID, they want to deploy vaccines to the population, but there's no data yet. And then you want to see hypothetically which of these vaccine is going to work in the population. So they will develop a model and then put the vaccine parameter into the model, and then they will give range from 0 to 100% of efficacy. So they will test it on the model. So while testing it from 0 to 10%, 20% efficacy, 30%. So maybe they have candidate vaccine, like 2 or 3 or 4 vaccine. They will test it on the model. So before they eventually launch the vaccine, so they use it as a clinical trial instead of trying it on human being. Do you understand me now? Instead of saying that we are gathering 20 people and you say we put them on placebo, and then you put some people on the vaccine, you are testing, and then you are comparing those people that were not vaccinated with people that are vaccinated over a certain number of days. You know, that's the way they do clinical trial. So, and then you now see at the end of the day how the vaccine is, how their body is responding. So, because that one is more expensive to do and it's risky, right? So, but this one is cheaper, cost effective, and it has no risk. The only thing you need a good brain and a good laptop. Yes? So, now it's cheaper, and then from there you are able to uncover the success and the pitfall of the treatment as well as the vaccine. Now, recent years have seen an increasing trend in the number of publications, both in high-profile journals and more generally that utilize mathematical models. A lot of publications that I was saying yesterday is increasing exponentially. How many minutes? No. 10 minutes more. You're supposed to tell me, I'll fire you. So, okay, help me watch. Can you give me my phone so that I can take note of the time? So, this is associated with an increasing understanding of what model can offer in terms of prediction and insight. Now, people are beginning to find, in fact, most especially after COVID-19, during COVID-19 and post-COVID, people started finding modeling as a very useful tool, because during COVID, there were a lot of, people were using modeling, because you cannot go to lab. Everybody cannot go to lab. So the only lab you can enter is modeling lab. You have your computer, you have your data, you start working from your home and sending out results. If you go to John Hopkins platform, then you see a lot of data on COVID. And immediately after COVID, do you know what happened? One of the effects of post-COVID era was that there were a lot of grants that were launched out on modeling all over the world. Even till date, a lot of grants on modeling projects. So now, what's the future now? The future is modeling and analytics. I must tell you the truth. The future is modeling and analytics. Yes. So any model can be typically thought of as a conceptual tool that explains how an object will behave. That's a simple way you can look at it. And then how an object will behave. So you start from the word concept, the idea. And then a mathematical model uses the language of mathematics to produce a more refined, precise description of the system. So that was why I said, if your model is more complex than the real world, then there is a problem. So in epidemiology, models allow us to translate between behavior at various scales. What do I mean by that? Scales. It could be time scale, because now the scale you are using in your model depends on the data you have. Now, most time it may not be time scale. If it's a cross-sectional data, you don't. Eh? Yeah, no problem. 722. Okay. So, ID. Okay, don't worry, because this time is not correct anyway, but I will use it just for the 10 minutes that you gave me. So, now, the time scale may not be, if you are working on a cross-sectional data, how many of us have worked with cross-sectional data before? Okay, can you explain the cross-sectional data for us? Can you give him a mic, please? We need a mic here. See mathematics. So when you can take a gradient, no, you will just bend down. You just differentiate, and then you reduce. You go. Yes, you reduce. X squared become 2x. 2x become what? 2. 2 becomes what?
So a cross-sectional data is data collected at a point in time. At a point in time.
Okay. So you hear that? Now you are collecting it. Give an example. That's a theoretical definition.
Yeah. An example could be we are trying to check, for example, in Boko town now, let's say we want to find out about the prevalence of malaria.
Okay.
We just maybe you send out a questionnaire to find out maybe in the last 2 weeks have you been infected with malaria? Anybody that says yes, and then in the last 2 weeks, anybody that says yes, among the sample that you have, you just find the
And everything have been collected today.
today. Yes, every can be collected today at a point in time.
Do you understand? So for that, the time scale is not time. It's not over time. It could be over age, the demography. That is, the number of people infected is over age, not over time. Are you getting me now? So your data will not read time evolution. Right? So that's the point that I want to make there. Yes? So, or you extrapolate from a known set of conditions to another. So as such, models allow us to predict the population level epidemic dynamics from an individual level knowledge. Now when you say population level epidemic, that means how the disease is spreading in the population start from one person. When I mean individual level knowledge of epidemiological factors, the long-term behavior from the early invasion or the impacts of vaccination on the spread of infection. Now, models come in a variety of forms, from highly complex models like the jets, the aircrafts, that is constructed with a lot of ideas. From that one is a multidisciplinary thing. People come from different discipline to develop a jet. It's not something you just sit down. Like somebody, a student in Nigeria he said they develop a jet, and then the professors that taught him, they wanted to, they didn't know, so they were entering the plane. So when they were entering the plane, the jet, and the guy said, so somebody was trying to introduce the person that developed the jet. Said, "Is one of your students?" "You mean you are one of my students?" As the professors wanted to enter the plane, they said, "If you are one of my students that did it, I'm not sure it's going to be." So they came down from the jet because they are sure of what they taught him may not be able to produce a jet. You don't understand? Yes. You see, let me tell you, one of the fear in Nigeria is that the government don't trust us. All of us that you are doing ASU, say they didn't increase your salary, this, that, that. The government does not trust you. So why? Because they have seen some people they got some grants at certain time, they went and used it to finish their house in the village. So that's why there's no trust. So if you say, or another thing is, okay, we are producing students. You hear now? The test of any professor or university is the student, your product. Now, the product you are producing, they cannot write a test to get a job. So you are now clamoring for, we need increment in salary. They will not listen to you. Because if they have found our product, they will get a job here or anywhere. Once you finish, you can fit in. Now, when you have to employ a graduate now, you have to, that's how they introduce graduate trainee. Why do you think they introduce graduate trainee? You think it's a good thing? When they are doing graduate trainee, it's because you don't know anything. They are trying to do a packaging on you, a panel beating, before they employ you. You think it's a good thing. You are happy. I'm a graduate trainee in First Bank. You are moving your hand like this. You didn't know that it's a shortage. Because you are supposed to be paid maybe 500,000. But because you are graduate trainee, they will be giving you 150. So you'll be, I thank God, I'm not a graduate trainee. It's in Yoruba, I call it Okpearun. The thanksgiving that is sick. You don't understand? Sick thanksgiving. Because when you are supposed to be on advanced level when you finish. But now we now have to retrain you You know, we were to train some GIT students. Among them, they were first class. In fact, top first class in the university, in their university, top. But you could not pass our exam. And what is that exam? 100 level question. They could not pass. But first class, 4.78 or 4.7 something. Best student. That's the question. Could not get 50. And 50 is not even a pass mark. You know what we are talking about. So the thing is, so there's no trust. So the professor said, oh, we know what you taught you. We cannot, we can't enter this place. Before we reach the next place, the thing will crash. So they left. So now, we need a range of experts to create and maintain them to simple toy models, like a bicycle, you know, that can easily be understood, modified, and adapted. Now, there are simple models like that. SIR, quickly do it. You can publish 50 papers within 1 week. And they put your name on the picture of your school, the best researcher. But everything you have done is SIR model. We are just changing alpha. When you hear you change alpha over 2, alpha over 3, this one alpha over 4, this one alpha over 5, this one alpha, because they are 50, alpha over 50. Then you produce in large quantities. So that one is not going to help the nation. Now, the decision whether to travel by bike or aircraft depends on several factors. I have 1 minute more. Such as time, distance, and cost. Now, if you want to travel by bike, will you save time? You are going to come from Ekiti to Benue by bike. Is it going to save time? Even if it's power bike. Will it save time? Now, will aircraft save time? Now, in terms of distance, which one will cover distance faster? The cost, which one is cheaper? So, if you are the one, which one will you pick? The answer is left for you. So, I will stop here. We'll continue.